everyone. I'm Prachi, and on behalf of Pune Knowledge Cluster, I welcome all of you to this 10th talk of Science and Technology series. This talk series we are having on the eve of 75th year of India's independence. And today we have with us for this talk, Professor Poonam Chandra. I would request my colleague, Dr. Disha Sawant, to kindly introduce our speaker for the day. Over to you, Disha.
Yes, thanks, Prachi. Am I audible?
Yes, you're audible.
Okay, so I'm here to introduce Dr. Poonam Chandra. Dr. Poonam Chandra is an astrophysicist and a fellow of the Academy of Sciences. Her research focuses on the end stages of massive stars exploding as supernovae and gamma ray bursts. Dr. Chandra completed her PhD at Tata Institute of Fundamental Research under the Joint Astronomy Program of IISc in 2005. She was also awarded the INSA Young Scientist Award for her PhD work. She was also a Jansky postdoctoral fellow at the National Radio Astronomy Observatory in University of Virginia, and then worked as a senior research associate and an adjunct assistant professor at the Royal Military College in Canada. Dr. Chandra is a recipient of the Swarna Jayanti Fellowship and is also a fellow of the Indian Academy of Sciences. So today we are thrilled to have her talk about evolution, energetics, and environment of energetic explosions, where she will be sharing her thoughts on the complex yet exotic life stories of massive stars and their deaths, which throw new light towards the mysteries of our universe. So over to you, Dr. Chandra.
Thank you, Disha. Let me first share my screen. And I hope I'm audible to you all.
Yes, ma'am.
All right, good. So I just want to minimize my screen. Okay, fine. All right. Thanks, Disha, for such nice introduction. I really hope I can convey a little bit of excitement to all the audience, as you have mentioned. So first of all, thank you so much to the Pune Knowledge Cluster for inviting me to give this talk, and I'm really thrilled to be, giving this talk. Unfortunately, I'm not in India, so it's nighttime for me, quite late in the night. But I hope I can, keep myself awake and all of you awake. So let's start with this. And as the title suggests, I'm going to talk about the evolution, energetics, and environment of these extreme explosions. And what I mean by these are some of the very exotic stars in our universe. So I'd like to start with this slide. And this is one of the most popular and important diagram in astronomy, and this is called Hertzprung diagram or HR diagram. One of the odd thing about this diagram is that the temperature increases towards the left, which is counterintuitive, unlike other plots where the quantities increase on the right hand side. But this is for historical reasons, and this is how it has been kept. And in this diagram, you see there is a strip at the center going from top left to bottom right, and that is called main sequence stars. Our sun also lies on this strip, and main sequence stars are all the stars which are generating energy by burning hydrogen into helium. And as you can see in this main sequence star chain, there are stars from bottom right, from red to top left to blue. And these in some way depict various masses of the stars, where the top left stars are the most massive stars and the bottom right stars are the least massive stars, and they are named as O, B, A, F, G, K, M. And in this talk, we will be focusing on mostly O and B kind of stars, which are the most massive stars, which you can see on the top side of this plot. Now, why are we doing that, first of all, and how does it connect with our topic? So let's just talk about first the sun. In the main sequence, you see there is this sequence of stars, and then you see somewhere I have written on the top right giants and on the bottom left dwarfs. So yes, you don't have to put your imagination to any stress, dwarfs are very tiny stars and the giants are very big stars, and they are basically nothing but different evolutionary tracks of the stars. So as inside the sun, hydrogen is burning into helium. Now, when the hydrogen gets exhausted, sun goes through some various evolutionary stages and becomes a white dwarf. And this is what life cycle of a sun kind of star will be. But if I take a more massive star, suppose a B kind of star, in that case, the track will be slightly different and it will make much hotter, much bigger white dwarf. And even the nuclear burning will proceed beyond hydrogen burning into helium. Now, how does this star important? This star is making a white dwarf. This star is not resulting in an explosion. But what happens? Suppose this white dwarf, which is of the mass of roughly around sun, but size of roughly around Earth. If this white dwarf comes in the vicinity of another star or companion, then because of the high gravity, this white dwarf will accrete mass from this companion. And if it reaches a certain limit, that is called Chandrasekhar mass limit, then this star, this white dwarf, will result into an explosion, and these explosions are called thermonuclear supernovae. So this is not a direct explosion of the star, but it is the explosion assisted by a companion. Now, if you take a much more massive stars, that's what we are interested in, or I'll be talking about in this talk. And here, one of the things you can already notice is this Betelgeuse. Betelgeuse is one of the big star in our galaxy. And just to show you the scale of Betelgeuse, that little orange thing is our sun, and this Betelgeuse is literally encompassing the orbit of Saturn, and this is how the big Betelgeuse is. And again, as you can see, Betelgeuse is not lying on the main sequence of the star, and because this is an evolutionary stage of a star. So what's happening in this case? Here, a 15 solar mass star is somewhere at the stage of Betelgeuse, but what's going to happen is that it's not going to stay here at this stage. In fact, if you may have read the news about Betelgeuse, you may have heard that people talk about that Betelgeuse will explode as a supernova any day, and that any day could be from now to maybe 4,000 or 5,000 years from now. But it is likely to explode as a supernova. And why is so happening? That's because suppose this is a massive star which is in the main sequence burning hydrogen into helium. Now, when all the hydrogen is exhausted, there is a core helium burning, and the star becomes very, very big, like a Betelgeuse kind of star. And now, the star is so big that the star has enough fuel and temperature and density to go to advanced nuclear burning stages, and to the extent that hydrogen burns to helium, helium into carbon, neon, oxygen, silicon, and finally up to iron. At that stage, something interesting happens. See, inside the sun, if there was no nuclear fusion happening because of the gravitational pull, the sun will collapse under its own gravity. It means this nuclear fusion is keeping the star stable. And this big massive star, when the iron was fused, iron is the most stable element. Now what happens is that there could not be any more nuclear fusion reaction. In that case, there is no pressure, radiation pressure coming outwards, and star collapses under its own gravity. Now, when it is collapsing, the density is increasing. At the core, the density becomes so high that it behaves like a wall, and whatever is hitting the star just explodes as one of the most energetic explosions in our universe. And this is called a supernova explosion. And that little thing which was remaining at the center, in some cases is a neutron star, and in some cases even a black hole could be formed. So this is a life cycle of the star, and this is what whole thing I will be talking today. And in this talk, I will be mainly focusing on the radio aspects of these evolution. One, radio is the lowest frequency of the electromagnetic spectrum, which in this diagram you can see the leftmost frequency. The second is that this radio observations do provide complementary information. For example, if you look at the sky on the left, it's a particular part of the sky. I will not tell you which part of the sky. I'll let you find out this part, and you can easily find out from the radio image. So on the left, if you look at the optical data, there is hardly anything which is interesting in this part of the sky. But if you see the radio, there is this big filamentary structure lying in the radio bands, and that tells us that there was something which optical telescopes could not see, but this event was emitting more radiation in the radio bands, and one could see these radiations. The third reason we prefer radio observations is that other than the optical window, radio is the only frequency which is transparent to Earth's atmosphere, which means we can build the telescopes on the Earth rather than going in the space like we have to do for X-ray and gamma ray and all other telescopes. Now, but there is one problem in the radio band. If you see on the left, this is the image of a moon, just a 10 centimeter optical telescope. Whereas on the right, there is an image of the moon with 350 meter radio telescope, which unfortunately is no longer there. But you see the image is very fuzzy and there is hardly any information there. And the reason for that is that the resolution is to be blamed. If you see the resolution of an image is wavelength over diameter. Now the wavelength in the radio case is much higher than the optical wavelength, which means the diameter of the telescope needs to be much higher. So even though the radio telescope on the right is 1/3 of a kilometer, still the diameter is not enough to reach the resolution. We needed to build, to have roughly the same sharpness of the image, we needed to build something like 30 kilometers of the telescope. Now it's very difficult or near impossible to build a single mirror of 30 kilometers. So this is where the radio interferometry comes into picture, where rather than building one mirror, we will build many small mirror, because it's much easier to build small mirrors. But now even this is very costly. So what do? We use the fact that Earth takes 24 hours to make one full rotation, and in that case we just build some telescopes, and then we use what is called aperture synthesis, which means we track the source, whatever source we are looking in the sky, we track the source from rise to set. So from source's perspective, it is actually because of the tracking, the antennas are seeing, the antennas from source's perspective, the antennas are moving. It means effectively many more antennas are tracking the source. And this is exactly what happens on Giant Meter Wave Radio Telescope, which is a telescope just 80 kilometers from Pune. It's in a village called Narayangaon, actually in a village called Khorat in Narayangaon. And this, you can see these white things in this image, and these white things are nothing but the telescopes. And if I show you the zoomed version, this is how these telescope dishes look. And there are 30 such dishes. They are spread over 25 kilometer diameter, and each of such dishes 45 meters in diameter, and they work at low radio frequencies. And what does these telescopes do? These telescopes, they track the source, as you can see in the bottom image, and as per the Earth's rotation, they are tracking the source, and then assuming that in this rise to track, the source property does not change. It means you can consider source to be same, and then you can try to, it means you can build a very sharp image using this radio interferometry and aperture synthesis technique. And this is what this telescope does. And currently GMRT is one of the largest low frequency radio telescope in the world. And I think if you have not seen the telescope, all of you should go and look at the telescope. It's really amazing and magnificent. Now let's come to the science part with this. So we'll first start with the massive stars evolution. And I've already talked about nucleosynthesis, but you can imagine just intuitively that some other ingredients which can affect the evolution of massive stars could be magnetism and binarity. And since we are focusing on the radio emission, and radio wavelengths are best tracers of the magnetic fields, today we will focus on the magnetic field part of the evolution. And there are two reasons for that. One is that, of course, we all know that sun has a magnetic field, and that's because the outermost layers of sun are convective, which means there is this dynamo action which is taking place and there is magnetic fields being generated. But massive stars have radiative outermost layer, which means they are not expected to or supposed to have magnetic field. But if you look at the spectropolarimetric survey of stars in our Milky Way, we find that 10% of all the massive stars are magnetic. They have this huge kilogauss dipolar magnetic field, very nicely, very stable magnetic field. And we know more than 50 such stars in our Milky Way. And these stars are very important because there are some highly magnetic phenomena in our universe which remains a mystery and we do not understand. One such phenomena is magnetar. How magnetars are originated, it is not clear. But magnetars are the objects with extreme magnetic field in the universe. Their magnetic fields are 10 to the power 15 Gauss, and there is no other such object which we know of which will have such high magnetic field. Other is magnetic white dwarf, which is also a very exotic object because these heavy white dwarfs are considered, if you remember just a few slides back, I had told you that these white dwarfs, when they come in the vicinity of a companion, they explode as supernovae. These supernovae are called thermonuclear supernovae, which are cosmological candle. These are the supernovae which have told us that universe is accelerating, expanding and accelerating. Now, if you do not have these standard candles, if you have these candles which have, some of them have magnetic field, one cannot use them as cosmological candles, and that's why it is important to understand them. So we are trying to understand the magnetic aspects in massive stars. And if you remember your undergrad physics, you will remember that a star, just by being a star, will emit a black body radiation. But the fact that a star is also losing mass from its outermost layer and creating a plasma around it, just like sun, our sun also has plasma. In this plasma, there will be Bremsstrahlung emission where electrons in the vicinity of proton will produce this radiation. Now, the fact that there is a magnetic field in the system, these electrons will accelerate, and because of this accelerated electrons in the magnetic field will also produce gyrosynchrotron emission. And then there is one more kind of emission, which is the exotic coherent emission. It is in some way the macroscopic analogy of the Maser laser emission. This is the coherent emission where a lot of particles are in phase and then they emit radiation in a low density environment. They emit radiation, all of them in single phase, and that generates a lot of energy. So that is, this is the electron cyclotron major emission, is the one which is a very exotic emission. And this is also exotic because in the year 2000, there was one magnetic massive star from which this emission was seen. And for 20 years, this remained the only star and no other second such a star was seen. But then we accidentally discovered a second star which showed electron cyclotron major emission. And then we understood the properties little more, and then we carried out a GMRT survey of all the magnetic massive stars. And I'm very happy to tell you that my student Bernali has discovered during her PhD thesis, she had discovered around 18 new such stars, and all of these stars in the yellow are discovered by this survey. So now we have more than, we earlier for 20 years, we had only one such stars. Now we have 18 such stars, which are producing electron cyclotron major emission. And this is extremely important because one, if you study these emission at various radio frequencies, one will understand where this emission turns on and where it turns off. And by studying a different wavelength, one can understand the magnetic topology of the star. Second, when this radiation is generated, it will pass through the plasma, and the way we will receive it will tell us how it has passed through the plasma, and that tells us plasma density. Now let me tell you, there is no other way in for anybody to understand the properties of the plasma or properties of the magnetic field so close to the star, but this provides a direct way to do that. Second is, if you happen to observe it after, say, some few years, in this case around 3 years later, you see that ECME, the emission peak has shifted, and that tells us that the star has changed its rotation period, which means suppose sun was emitting ECME, and suppose we observe the sun ECME every now and then, and we see the change in the peak, we will know that sun is not rotating at the same speed. Something is happening in the speed of the sun. So this is not possible so easily to measure such properties. Second, as you can see, this emission is so bright that we can actually see it from far away galaxies, further away galaxies also. We can try to understand the origin of magnetic field, how it has been generated, which remains a mystery. How this kind of magnetic field will behave in a binary system, which is also another interesting aspect which we are trying to understand using this. And then, of course, we are trying to understand the parameter space in these big transients space where these stars will lie, and what does it tell about the energetics and environments of these properties. So this is about the evolution of the stars. And now if you remember, a star will evolve, and then a star will go through these various fusion stages. Here the time scale I have shown is just for a 15 solar mass star, but if it was a 25 solar mass star, it'll have much faster evolution. Sun will have much slower evolution, and star, which is half the mass of the sun, will have even more slower evolution. So this is how it proceeds. But it will go through all the stages: hydrogen, helium, carbon fusion, neon, oxygen, silicon, and then iron, the last stage. Now, what is going to happen? This is a very interesting aspect. If you again remember, after the iron, it will explode as a supernova. Now, there are two interesting things happen when this explodes as a supernova. One, the supernova explosion, of course, which is very energetic explosion. But second, all of these heavy elements which were formed inside the star now are scattered in the medium around it. And that is how, suppose a new star system is formed in that medium, that star system will already have these heavy elements. For example, our sun, solar system already has all these heavier elements, which makes the possibility of life real. If there were no such stars, no massive stars in the universe, there will not be oxygen for you to breathe. There will not be calcium in your bones. There will not be any aluminum in the car. So all of these heavier elements are made inside these stars, and this is how they're made available to us, and this is what we owe our existence to. So this is how these heavier elements are formed. And then, of course, starting supernova explosions are also interesting because these are really the physics happening at its extreme, where we're talking of the relativistic velocities, extremely energetic events. These supernova explosions are so energetic. Suppose you take our Milky Way. The Milky Way has 200 billion stars. One massive star explodes as a supernova, that will outshine the whole of Milky Way stellar light due to all the 200 billion stars. This is how much energy being produced in one supernova explosion. So it provides us a very important and very only way to study the physics at its extreme. Now, how do we find the supernova? If you look at this animation on the left, you will see there is a galaxy. There is a supernova appearing, then becoming dimmer. We can look at the light curve of the supernovae, and then we can look at the spectra of the supernovae. We can try to understand. But finding the supernovae is not that easy. Why? Because they are just coming and then going, and it's unless one keeps on looking at the sky at a particular position, it's very difficult to find the supernova. And that is the reason earlier very few supernovae were known. So if you look at this animation, the thing which is changing, these are the year number, which year. So if you can see in early 1900, maybe just a few supernovae were known. But now many more supernovae are known because the technology has advanced so much. There are so many robotic surveys which are looking at the sky every night and looking for the difference, looking for anything new coming up in the sky, and then once something new is seen, the spectra is taken, and if it looks like a supernova, then a supernova is discovered. And this is how supernovae are found. And now when we look at the supernovae, we look at their spectra, we look at their light curves, we find that there are tons of kinds of supernovae, so many that we can't even keep track of. The problem is that we find tons of supernovae, and looking at the spectra, we also know that some supernovae did not have hydrogen, supernovae did not have helium, some supernovae had hydrogen and helium and everything. But we don't know which kind of star exploded to become which kind of supernova. So what is the use of physics if we can study something but do not understand where in the evolutionary process does this lie, or which kind of star is evolving to become this kind of supernova? And again, that's where radio emission is very important, and we call it understanding the supernova progenitors using time machine. And I'll tell you how this happens. So suppose this is a star, and then the star is losing mass, which you can see on the surrounding the star. And eventually after, evolutionary phases, this is how you will see at the center, you will see this a star which has exploded as a supernova, and then surrounding the star, this is the plasma. Now, what is the plasma? This plasma is again this stellar material which was lost from the outermost layers of the star because they were least gravitationally bound. So now this is how a picture appears. There is this plasma or wind, which is created by the mass lost from the star. And then the yellow part is the ejecta, which is the explosion ejecta. Now the interesting part is that while ejecta is moving the supersonic speeds, so it is moving into this wind, and then it is, tracing different distances. What you need to notice is that if it is going further away, this is the wind which was lost from the star much before the explosion. So if I am, and then if you keep on tracing this wind through the ejecta, it is lost much before explosion. And now the interesting part is that the wind speed is only 10 kilometers per second, the plasma wind. The shock speed is supersonic, which means the ratio is 1000. What does that mean? That means that if you look at these different fusion stages, now look at this again. If this is where my shock has reached, say 1 day after the explosion, and I'm looking with a radio telescope, I'm basically looking at 1000 days before the explosion, how the star would have looked. If I'm looking at, say, 1 year after the explosion, I'm looking at 1000 years before the explosion. Or if I'm looking at 10 years after the explosion, I am actually looking at 10,000 years before the explosion, how the wind would have looked or the star would have looked, which means I am able to trace the different evolutionary stages of the star before it exploded. And that's why I call it a time machine. And this is a more, scientific diagram where this is the gray part is the wind and the blue part is the supersonic ejecta, and it is giving rise to synchrotron emission, which is again the relativistic electrons in the presence of magnetic field is giving rise to this emission, which does tell us about different kind of progenitor. And we have been carrying out GMRT survey of these supernovae to understand these things, and there are many interesting things we have understood. One thing you have to remember is that GMRT is a low frequency telescope, which means in this synchrotron, it is tracing the left side part. But this is the left side part, which is the most interesting part because this depends upon the density. It means it tells about how the plasma is looking, how the plasma of the star is behaving. So when we study various kind of supernovae, what we are seeing is that this wind is not really, that smooth as the models will tell. It is not a spherical cow. There are these winds are very, bumpy, and The star is not losing mass at a very smooth rate. It is having ups and downs, and then those things one can look in the radio observations. Second thing is that radio observations, if you model the peak of the radio light curve for the spectra, you can see the velocities of the shock. Now, shock velocity is determined by how energetic the explosion was, how fast the shock is moving, and that tells us what kind of star could be, what kind of compact remnant could be found at the center, what kind of energies it is producing, what could be the nature of these things. So this tells us about the central engine of the star. The way the spectra looks, the way one can also do very long baseline interferometry observations of these stars, which are micro arc second resolution, because you put one telescope in, say, Pune, one telescope in Bangalore, one telescope in Delhi or something like that, just concept wise. This image, the center image, is from such telescopes put in various places in the United States. And if you look at these images, it tells us that progenitor was not a single star, the progenitor was a binary star. So it does tell us about the nature of this supernovae progenitors. So radio observations does tell us about these different kind of progenitors of the evolution. Now moving on, I think I still have some time. Yes, I would like to tell you about another exotic explosions, and these are called gamma ray bursts. So this animation, this is what we have seen. These are the supernova explosion. The star runs out of its fuel, and then core collapses, and gravitational collapse of the core leads to the explosion. Supernova happens. But what if the star was, and then of course there is a neutron star which is formed at the center. But now what if the star was much more heavier and it did not form a neutron star, but it formed a black hole at the center? In that case, an accretion disk will be formed. Perpendicular to that accretion disk, all of this matter will come out, and this matter, because of the relativistic effects, will be very, very highly collimated. So now what is coming out is very, very collimated, very, very directional emission. And I'm going to see only if I am sitting here, or Earth is in this direction. If I'm sitting somewhere else, I'm not going to see this. So these are basically supernova explosions, but highly directional. And these are coming from much more massive stars, and these are called gamma ray bursts. And these are so far the most energetic or most extreme events in our universe. And to give you a sense, on the left is our universe in the gamma rays. And now this event is happening for just 2-3 seconds. In that 2-3 seconds, this one single event from one star, say 130 solar mass star, is outshining rest of the universe in gamma rays. This is how energetic this event is. But there are few things. Gamma rays are very hard to focus. You are going to see this event only if it is pointing towards you. And third thing is that they are lasting only for 2-3 seconds in the sky. So how do we find them? And that is a very difficult question and very difficult problem to solve. But thankfully, there are some telescopes, space-based telescopes, gamma ray telescopes, which keep on scanning the sky for these events and keep on finding gamma ray bursts. And many such gamma ray bursts have been found. We have thousands of gamma ray bursts, which means there are actually at least 500-600 times more than what we have found, because we have found the ones which are pointing towards Earth, but the ones which are pointing away from Earth, we have not seen those gamma ray bursts. So there may be many more gamma ray bursts, and then these events are just lasting for a few seconds. And in fact, that is the reason these events were discovered in late 1960s. Before that, nobody even knew that they exist, because it's so hard to detect them. But thankfully, they have low energy counterpart, which we call gamma ray burst afterglows. So what happens? This ejecta, which is very, very directional ejecta, when it moves through this medium, plasma, it produces synchrotron radiation, which will be there in all the wavelength from gamma rays, optical, X-ray, optical to radio. So this is how, again, I'm showing you an animation. Remember, none of these are real animations. We just depict the physical picture that what is happening. You don't see these things in the sky. They are so far away. These gamma ray bursts are so far away that you don't see all. You will see something like this. And this is actually a real image of the gamma ray burst at, taken within like several times within few days. And this is what you see, and you just have to infer the physics that something like this is happening. And I'm going to give you, so this radio observations again are very important. One radio is here, if you remember, this is the synchrotron low frequency. It means radio has a slower evolution, which means one can look at these gamma ray bursts. If I was a gamma ray astronomer, I will have to actually be awake almost all the time just to look for these gamma ray bursts, because they will last only for a few seconds. But as a radio astronomer, you can have your good night's sleep. You can still keep on observing this, because in radio band they will last for weeks to months and sometimes to years, because they're so slowly evolving. And from early time radio observations, one can constrain the density. Sometimes one can constrain the Lorentz factor. If you can do a micro-arc-second imaging, then one can constrain the size of these gamma ray bursts. If you take the late time radio observations, at that time, the emission is gone in all other wavebands. It is only the radio emission which one is seeing. So then one can study these for a very, very long time. And this is one such example I'm showing you, where the radio data has been taken and combined with other wavelengths. One can constrain the energetics, density. But what is so interesting about this particular gamma ray burst is that this is at a redshift of 8.3, which means this gamma ray burst explosion happened when universe was only 0.6 billion years old, and this radiation reached us in 2009. So this is one of the earliest gamma ray bursts with radio emission. And this tells us about the universe at that time, what kind of density was around this GRB gamma ray burst at that kind of redshift. And it also tells us that the stars were forming and exploding at that early universe. So it actually gives us a lot of information. So this is about gamma ray bursts. And so basically the explosion of massive stars have happened. And what is remaining now? And what is remaining is that we have very little time remaining, but in that little time, I would like to tell you that after death, things do not just die out, things still remain interesting. And what happens is that there is a central neutron star which remains in these core collapse supernova explosions or gamma ray burst explosions. It will be neutron star in supernovae, or most likely a black hole in gamma ray burst. And how do we look at these stars? Of course, neutron stars, we all know. We look at the radio pulsars. There's tons of pulsars. There are thousands of pulsars in our universe and in our Milky Way. And radio telescopes have been looking at these pulsars left and right. GMRT has been discovering so many pulsars and studying these pulsars. And what are pulsars? These are just rotating neutron stars. But now my question is that how do we detect a black hole? Black hole is not going to emit any kind of light. And we are seeing neutron star because it is rotating and it is emitting light in radio bands, but not this black hole. So how do we detect the black hole? And here things start to become even more interesting. You can detect the black hole if there are two black holes together. Because when the two black holes together, they spiral in, they merge, and they produce what is called a gravitational wave. And gravitational wave is what? It is the ripple in the curvature of space-time itself. This is happening due to acceleration of two masses. Here the two masses are your black holes. Because of these acceleration of the masses, these gravitational waves are being generated. they're creating the ripples in the space-time. What does that mean? Space-time itself is moving. It means if you look at this again, the Earth itself is changing its size, even though this change is very, very little. But if one can detect these changes in the size in the Earth in one direction, the way gravitation waves are passing, then one can understand or study the presence of these gravitation wave. And this is exactly what happened in 2015. This is this advanced laser interferometry gravitation wave detector, which is nothing but Michelson-Morley interferometer, where there are these two mirrors. These are these 4-kilometer arms. Now they are in phase, but when a gravitation wave passes, they are out of phase, and then you see this fringe pattern. And this is exactly kind of fringe pattern which was seen in 2015. And from that, scientists figured out that two black holes of around 30 solar masses had merged, and they produced gravitational waves. So while there was no light from this merger of black holes, there were gravitational waves, and these gravitational waves were detected with advanced LIGO. And because of this, a Nobel Prize was given in 2017 for the discovery of gravitational waves. Because one, it was extremely difficult to detect these gravitational waves. These LIGO arms had changed only by 1/10,000th of the width of a proton. So that little change was measured. Second, this was one of the last predictions of Einstein's general theory of relativity, which had finally come true. So that's why in 2017, Nobel Prize was given. But another interesting thing happened in 2017. What LIGO saw was merger of two neutron stars, which produced gravitational wave. It also produced light. So what that means is that for the first time in the history of mankind, we have seen an event which produced gravitation wave as well as light, electromagnetic radiation, all the way from radio, optical, X-ray, and gamma rays. And almost everybody who was even slightly interested in gravitational wave studied this event. This remains the single most such event. It was truly a watershed event in the history of Earth, and the kind of studies which were done were unprecedented, because you can measure the distance using gravitational wave as well as from the electromagnetic radiation. One could see that gravitational wave move with the speed of light. One could also constrain the Hubble constant. When supernova explosions were happening, people were studying that while supernovae can explain the presence of iron, calcium, oxygen, they could not explain the presence of heavier elements like gold and platinum. And from this event, it got confirmed that when this neutron star merger happens, this highly neutron-rich ejecta can produce these heavier gold and platinum. So by studying the spectra and light curve of these event in the optical band, we got to know that the gold and platinum in our universe is being produced in the mergers of two neutron stars. Another thing is that while so far I have talked about a gamma ray burst, where a 30 or 40 or 50 solar mass star is making a black hole and creating this gamma ray burst, this event told us that there is another way to make a gamma ray burst. And what is that way? That you bring two neutron stars together, they will merge to form a black hole, and that will also create a jet. And here the radio observations were very useful. We literally used every single radio telescope on this planet, and we carried out the observations for actually years too after the event. We also carried out the micro arc-second resolution image. And what we found is that early time, the radio emission was coming from this medium which was disturbed by the jet. But later on, eventually after around 75-80 days, the jet broke out of this medium and then gave rise to a gamma ray burst. So this event it was literally a plethora of information. It told us so much that no other event has told us so far. And this basically tells us that such extreme events are happening in our universe, and sometimes you will see them in electromagnetic radiation, sometimes you will see in the form of gravitational waves. So what do we have? We have another messenger of information. And why is this important? And this brings to the end of my talk, is that we know if you, this is basically the, what to say, how our universe is formed. Whatever we are talking about, whatever we can contemplate, all the galaxies, all the stars, in between the stars, everything. This is just 4% the matter. The 1/4 of the universe is dark matter, which behaves like gravitationally, like a gravitation object will behave, but no light has been seen, or it does not emit any light, electromagnetic radiation. And then the dark energy, which we just don't understand, but it makes 2/3 of the universe. So now we have been studying astronomy, not just in radio bands, radio, optical, X-ray, gamma ray, but these are all photons. They tell us about universe. We also have neutrinos, but now we have another messenger of information, which is gravitational waves, and this will bring the information there from the things which will not emit light or neutrinos. So which means we are one step closer to understanding our universe. And I would like to tell all the young audience that in this field, currently it is really a golden time to do astronomy in India, because one, I have already told that we have this GMRT telescope, which is just 80 kilometers from Pune. In addition, India is also part of what is called a Square Kilometer Array, which is an international project of radio telescope, where one set of telescopes will be in South Africa, one will be in Australia, and this is a multi-country telescope, and India is a major partner of this project. Then we have a lot of good optical telescopes. We have 3.6 meter Devastal telescope in Nainital. We have Himalayan Chandra telescope, 2-meter telescope in Hanle. And then India is part of 30-meter telescope, and which will do some really amazing science. This is one of the largest optical telescope conceived on this planet. Then in high energy astronomy, we already have AstroSat, which is working from ultraviolet to gamma rays, and it also has a polarization capability at hard X-rays. There is also another project which is coming up by some folks at IIT Bombay and Ayuka and other places. This is called Daksha. It is going to be a very, very efficient and sensitive high energy gamma ray telescope looking for gamma ray bursts in the sky. Then we certainly have LIGO India, and LIGO India is going to change the face of gravitational wave astronomy, because if you see on the right hand side in this plot, these are the error circles of the gravitational wave event. But once LIGO India is built, then you will be able to find this gravitational wave in very small areas, which means you can point your other telescopes and look for the electromagnetic counterpart of these telescopes. So basically, India is right now at that juncture where in all the wavelengths in electromagnetic spectrum and the multimessenger astronomy, a lot of things are happening, and it is really the right time to get into the astronomy and study not just this field which I talked about, but many other fields. And I think at this point, I will stop this presentation and take any questions. And I hope I have not gone over time. Thank you so much.
Thank you, Dr. Chandra. We have Professor Ajit and Disha with us. So would you like
Hi,
to...
Ajit.
Ajit sir, can you hear us? I think he's traveling, so maybe his network is feeble. But Poonam, that was a wonderful talk, very illustrative, and we loved the graphics, and because of which we could understand the subject much better. It was very much thrilling to learn all the information about these explosions. So
Yeah.
Thank you so much.
Ajit sir is here. Yeah.
Yeah. Okay. Hi, Poonam.
Hi, Ajit.
Hi,
so Ajit.
I'm actually on a country road, but I managed to take in about, and then I actually fell asleep as soon as I woke up. I saw your talk, and I took in about 20 minutes. So it was really very nice, and you blended so many things together so seamless. So we're very happy to have this talk. Thank you very much.
Thanks.
Okay, thanks, sir. So there are questions from the viewers and audience. They are asking that you mentioned about gold getting generated from such explosions. So does that mean that that is the only source of all these valuable elements that we found in Earth?
So far, we have confirmation of only that neutron star mergers can make such heavier elements. Basically, if you look at this, if you remember this table, this here, maybe I should just, if you look at this periodic curve, all these orange things, these are the things which supernovae are, it's incapable of producing. And we were looking for something like a neutron star merger, which, because you need a lot of abundance of neutron rich elements, and that is what exactly is the favorable condition. And right now we don't know anything else where it can be produced.
Right. So it's a high possibility that we are somewhere part of these supernovae or some gamma rays that happened in the past.
Of course, yes.
Wonderful. Okay, that's thrilling to know. Also, there is another question. From radio observations, are there any peculiar features that can be drawn which are not found in any other spectrum or any other media of observations?
Yes, so there are a lot of things. One thing is synchrotron emission is mainly generated in radio bands, and the reason is that you need relativistic electrons and a presence of magnetic field to produce synchrotron. Now, not just any relativistic electrons will produce. If you have to do radio emission at say 1 gigahertz frequency, the electrons have to reach to GeV energies, giga electron volt energy. Now the electron has a rest mass of 511 kilo electron volt. Reaching to GeV is not a easy thing to do. So which means the chances are that these kind of synchrotron emission will be always be dominated by the radio emission. So that kind of a thing you are going to see. So, and since these involve relativistic electrons, basically you are going to see the physics which involve these high particle accelerations in our universe.
I see. Okay, thanks. And doctor, there is another question that mentions that since these explosions are so massive and gigantic, should we be worried?
So I had, or not just me, a lot of scientists had once done a calculation, and they figured out that if something is happening, say 30 kiloparsecs away from us, then we will see some effect on the ionosphere of the Earth. Not to wipe out the life on Earth, just the effect of on the ionosphere. So right now, the only candidate which is nearest candidate of explosion is Betelgeuse, which is 500 parsecs away. So we are quite safe. So did I say 30 kiloparsec? I think 30 parsecs. Yeah. Okay. So this is so we are quite safe. So I don't see any immediate threat to our existence.
Right. Okay. Gayatri, are there any? Yes, other questions?
Yeah, we have one more question by Deepali. So she's asking that, like we have a particle of light as photon, will there be any, or is there any particle for gravitational wave?
You can name whatever you want, but yeah, some people say graviton, but but what we know is that yes, gravitational waves are another form of not radiation but messenger, and the way their frequencies are, people call it that listening to the universe through gravitational waves, whereas the photons are like looking at the universe using electromagnetic radiation. So that is the analogy I can give. And then gravitational waves certainly travel with the speed of light, which is the maximum speed physics so far a standard model allows for us. So that's all I can say. Yes.
Sure. Okay. So wonderful. We have reached to the end of the session. May I request all the participants to just turn on their videos so then we can have a nice group photo with Dr. Chandra.
So I'll stop the sharing.
Yeah.
Okay.
have we allowed participants to share their video?
Yeah. Wait, Disha, I will change it. Yeah.
We have to just change that.
Participants, can you please try to turn on your video? Yeah, I think it's working.
Yes.
We request all the participants to please turn on your videos. I think, Disha, I have taken a screenshot, so
Okay, perfect.
we can close the session.
Sure. Okay, so on that note, we would like to thank again Dr. Poonam Chandra. Thanks for the wonderful session. It was a great start for the weekend for all of us. And we look forward to have more such collaborations and lectures from you for Pune Knowledge Cluster.
Sure. Thanks. Thanks, Disha. Thanks, everyone. Thanks,
Thank you.
Gayatri and everyone.
Thank you.
Thank you, Professor
Yeah.
Chandra. Thanks.
Yeah. Bye.